Right then, so welcome to Aromatic Lesson 3, Nitration of Benzene. It's quite a biggie, this one. So it's our first proper sort of reaction of benzene or benzene derivatives. So we've got some starter questions. Pause the video and have a go at these. Pretty much all revision. Okay, so we should have cracking equation that looks like that. Reduction equation with 2 moles of the reducing agent, which is NaBH4 in water or aqueous solution. Your esterification reaction should look like that, and you would warm it with conc H2SO4 as a catalyst. The yield for this reaction, I did ask about that, the yield for this reaction would be poor because it's reversible. It's a dynamic equilibrium, and you don't necessarily get a decent yield of the ester because it instantly hydrolyzes back to the carboxylic acid and the alcohol. Then for the challenge question, isomers of propyl butanoate. Most obvious example is to go for locating the ester linkage and moving it somewhere, so basically position isomers. So the first molecule was propyl butanoate. The second molecule that I've drawn a green circle around the ester linkage for is butyl propanoate. And then you can basically move it around and get several other combinations that are written there. I didn't draw them all because obviously it gets to be a little bit time consuming. Then something else you should realise is that you can have the functional group isomer of an ester, which is a carboxylic acid. The most obvious example here is heptanoic acid, but obviously you can branch this too. And so if you take away a couple of bits, then you could have a branched carboxylic acid that would also be an isomer of that same molecule. You could also branch the ester as well, although I didn't look at any of those. Right then, on to it. So here are the facts, right? Nitration of benzene. You can nitrate arenes. If we're saying that nitration is a verb, you can nitrate them. You do that by adding a nitro group. This is the first and only time you'll see the nitro group in A-level chemistry. You never see it anywhere else really, but it looks like nitrogen and 2 oxygens, NO2. So in brackets there we've got the bond to something else, and that's attached to the N, which is then attached to 2 oxygens. So the reason that we care about nitrated arenes is that they are precursors or starting materials for explosives. And something else that we look at is that you can reduce them to aromatic amines. So pause the video as appropriate and take your notes. Then let's have a look at an example of a nitrated aromatic compound. That's a very famous one. So this thing is called trinitrotoluene by most people, or TNT for short, which is obviously a very famous explosive. Its UPAC name is 2,4,6-trinitromethylbenzene. So just to be clear, this bit, the trivial part of the name, toluene, that is what most people who aren't following UPAC rules call methylbenzene. The methyl group is occupying position 1, which makes the nitro groups at 2, 4 and 6. That's where the naming sort of, or the numbering in the name comes from. So let's have a look at how the nitration reaction works. It occurs via a mechanism that we call electrophilic substitution, or electrophilic aromatic substitution it's sometimes called. The aromatic bit is not strictly necessary for naming the mechanism, so I've put it in brackets. To make this happen, you need a reaction mixture of benzene or a benzene derivative, like methylbenzene for example. Whatever your aromatic compound is, you then mix it with concentrated sulfuric acid and concentrated nitric acid. And there's actually quite a lot going on here, and that's why we need to sort of take our time with introducing the mechanism. So before we do look at the curly arrow mechanism for this reaction, we have to consider what happens when you mix conc sulfuric and conc nitric acid. This stage is sometimes referred to as generation of the electrophile. So what we're doing here is we're talking about how these two acids react together, and one of the things that they make is the electrophile that we put in our mechanism, our electrophilic substitution mechanism. This can be a little bit complicated, so let's have a look at the relationship here. You've got conch sulfuric mixed with conch nitric acid. You're going to get two products in this equation. There's actually different versions of it which we'll look at in a minute, but in this version we're going to get two products. So both of these things are acids, but concentrated sulfuric acid is a comparatively stronger acid, and acids are proton donors. So what we're basically saying is that concentrated sulfuric acid is a more effective proton donor than nitric is. What that means is, in this reaction, the products will be a hydrogen sulfate ion, and that is the kind of product of the sulfuric acid having donated a proton. It's lost H+, and so HSO4- is left behind. You should be able to deduce the structure of the other product, so have a go. What we should have arrived at is a positive ion, H2NO3+, and that is basically nitric acid that has been protonated. So let's clarify something here. The role of the conch sulfuric acid is that it's an acid, which might seem really obvious, but actually, because of the fact that the nitric acid is acting as a proton acceptor, that means that it acts as a base. So let's just let that sink in for a minute. Concentrated nitric acid in this reaction acts as a base, despite the fact that it is a concentrated acid. This has to do with the relative acidity of conch sulfuric and conch nitric, and because conch sulfuric is comparatively stronger, it acts as a proton donor, which means that the nitric has to act as a proton acceptor. So that's a little bit weird. So we still haven't technically generated our electrophile. Let's have a look at what happens to that protonated nitric acid, that H2NO3+. So we can kind of consider that to spontaneously decompose into NO2+ and H2O. This is the most important bit. This thing is our electrophile, and it's what's going to appear in the mechanisms. It's called a nitronium ion. Now, overall, generally people do this in one equation, so let's have a look at what that looks like. This is the version you should probably learn, by the way. So you've got your sulfuric and your nitric. You can get your hydrogen sulfate ion and the electrophilic nitronium ion, NO2+, and water. That's effectively the combination of the two equations that I showed you, where you cancel out the H2NO3+. You might be wondering why we bothered doing that at all, and why I didn't just give you this equation in the first place, and the reason is to explore the idea that the concentrated nitric acid acts as a base, as a proton acceptor. It's a bit easier if we go through it to make that H2NO3+. So there's your equation to generate the electrophile. That's a very common sort of opening part to a question about the mechanism that then follows. So, speaking of the mechanism, we have our electrophile, we have a benzene ring. It's just plain old benzene, not methyl benzene or anything like that in this case, although it could be. So, we're going to have one curly arrow, and remember, the curly arrow always moves from a region of high electron density, or originates at a point of high electron density and ends up somewhere with a low electron density. So in this case you should be able to suggest how the curly arrow fits in. What we get is a movement of a pair of electrons from within the ring of delocalized electrons to form a bond between a carbon on the outside of the ring and the nitrogen in the nitronium ion. Effectively what happens here is the ring of delocalized electrons is broken open, and we'll see what that looks like in the next step. So, this structure is an important one. It's often referred to as the horseshoe when they're sort of discussing it in mark schemes. what it basically shows is that the ring of delocalized electrons has been broken. There's a positive charge in the middle because the carbon has now kind of lost access to some of the electrons that have been used to form a bond to the nitrogen. The little green dots here are just for me to point out that often there's a comment about how big the horseshoe is. Basically, it shouldn't go any further than those dots. It doesn't matter if it's a little bit smaller. So that green line there ends up looking like a bit of a smiley face. That green line there would be okay, but that one would not be. It's too big. Okay, so they're a bit picky about how you draw that. My version is fine. So what now happens is the ring of delocalized electrons reforms, and we're going to need a pair of electrons to make that happen. We're trying to nitrate the benzene, so the only pair of electrons that's available is between the carbon in the benzene ring and the hydrogen that's at the top. That pair of electrons is going to be used to reform the delocalized ring, which is going to make the hydrogen leave as an ion. So that's our second and only curly arrow. And we end up with this. So we now have nitrobenzene, benzene with an NO2 group. A hydrogen ion has been released. And it's worth pointing out that this is a sort of random-ish process. I mean, you can control it a little bit, but if you want to make the benzene ring nitrate only once, you keep the temperature low. If you want multiple nitrations, you need to increase the temperature. So you can obviously get trinitrobenzene, we saw that earlier on. And to do that, to encourage that to happen, you would need to raise the temperature. If we have a look at this equation, the hydrogen sulfate ion that's hanging around can then basically pick up, I suppose, the hydrogen ion that's also hanging around and reforms sulfuric acid. This is an important concept in organic chemistry that we look at a lot. The sulfuric went in at the beginning and it came out at the end unchanged overall, which means that it is catalytic, it's acting as a catalyst. So that's the role of the conch sulfuric. The conch nitric is obviously not a catalyst because it does undergo a change, but the conch sulfuric is a catalyst. So then, we've got a practice sort of set of questions here. Okay? Let's say that we start with toluene, methylbenzene. I want you to name and outline each mechanism to show each nitration to form 2,4,6-trinitromethylbenzene. Then deduce the molecular formula of TNT, and then write an equation to show the thing that you've been asked to do down at the bottom there. Just to be clear, you should be drawing 3 mechanisms, and each time you should be adding one more nitro group. So it'll just be one nitro group to the next, in the first instance, then you'll be adding a second nitro group, then the third nitro group. And the position that they end up in is important. If you can't remember how the numbering works, go back to near the beginning when we looked at the structure of a TNT. So pause the video and have a go at those. Right then. We'll have one step here, a second step here, and a third step here. There's nothing too difficult about this because the mechanism itself is actually relatively straightforward. You just have to make sure you're being careful with where you attach your nitro groups because they needed to end up in the 2, 4, 6 positions. I went clockwise around the benzene ring. If you went anti-clockwise, that's totally fine. Doesn't make any difference because it's still going to be 2, 4, 6. The molecular formula for TNT is going to be C7H5N3O6. If you're not sure how to arrive at that, remember that benzene in the first instance is C6H6. Methylbenzene would be C6H5CH3 or C7H8. Then what you've got to consider is that every time you add a nitro group, you're taking away a hydrogen because it's a substitution reaction. So that means we end up with C7H5, and then the N3O6 represents the 3 nitro groups. I suppose you could have it like this. Effectively the same thing, but if we're just talking pure molecular formula, I've just bunched everything together so that you've got the number of atoms of each element with no reference to how they're bonded. So then, if you had to go at this, the balancing's a little bit awkward. 1 mole of TNT would make all these slightly awkward numbers. You might have found it easier to double everything and have 2, 3, 7, 5, 7. Doesn't matter which way around it's done, they're both correct, but it's just, it looks a little inelegant when you've got all these 1.5s, 3.5s and all that kind of stuff. So doubling it does make it look a little bit nicer. Right then, that's the lesson on nitration done.